What's up, everyone? Today we're going to talk about this problem. And in the previous video, we discussed this system where this is not LTI system, like directly LTI system, where A of t, like A matrix, a state matrix, and at each time takes values between or takes values from the sets, and then this set is this expression is convex hull. Okay, and then A1 and A2, right? So this is n by n. In this specific system, it was 2 by 2. Yes. So A of t, what is it? This is, yeah, 2. It was 2 by 2. All right. And this is the system. And then this was the Lyapunov function that we discussed. Now, for this Lyapunov function can to be used for proving the stability of this system, like this is called PLDI, Polytopic Linear Differential Inclusion. There are some conditions, like this feasibility problem, feasibility type optimization problem needs to be solved. And so the important part here that we need to discuss is the following. How come, okay, this is the system, I understand that, and this is the type of the Lyapunov function, although it is not the type of Lyapunov function that we are familiar with so far, right? I haven't covered something like that before, or I covered something like that and in my previous video, but this video is to clarify like some of the confusion or some of the steps that I didn't clearly explain before, and now we will look at that. So for this Lyapunov function, here we can see P1, P2. These are the parameters. So we need to basically determine P1 and P2, right? Okay. And for this type of structure, this is the, like, if you can recall, if and only if condition we have here, and feasibility type of problem that we need to solve. And if we are able to solve it, like if we are able to find P1, P2, and then lambda terms such that the given stated conditions are satisfied, then we can clearly state that this Lyapunov function proves the stability of this function, of this dynamical system, autonomous PLDI system. All right. So how did we get here? Like from here, right? And from here, we basically know the conditions. This is condition number 1. This is condition number 2. This is V dot. So positivity of the Lyapunov function and the negativity of the derivative, like time differentiation of the Lyapunov function. So basically from these two conditions, we arrive to these conditions. And this is like important thing to state is that this is asymptotical stability. I mean, this is good. And this is not quadratic stability. This system is not, not this system, or the system that I stated in the previous video, if you can recall, it was not quadratic stable. Quadratic stability, or rather stability, asymptotic stability, doesn't imply quadratic stability. And this is an important point. So this also shows that quadratic stability is a conservative type of stability, like condition. Okay. And another fact is the following: robust stability may not imply asymptotic stability, right? There's no need to discuss going into the details of like robust stability, but because this video in and of itself will be like with the content that we have will be quite long, and I will try to keep it as brief as possible. So now we will discuss how we can derive these conditions from these two Lyapunov type of criterion, right? So this is claim 6, and let's discuss that. I think it would be better for me to let's say, yeah, okay. So this is claim 6, and this is the final one. We have 1, 2, 3, 4, 5, 6, and this is the final claim. So I'm going to go over these 5 claims first of all, and then we will look into that, and it will make a lot of sense, all right? So let's okay. So first of all, you may be thinking, how did even we arrive to this set definition? But if you remember, okay, that will make sense in a minute. So claim number 1, we are looking at this, and P1 is strictly positive definite, P2 is positive semi-definite, and given these two matrices, we are considering the following set, where this is the set definition, is a huge definition if you notice. So we have, it's a set of matrices, like one by one, let's dissect, let's or analyze what that term represents. So A is an n by n matrix, okay, such that this condition is satisfied, right? This inequality condition is satisfied, and where the x terms comes from this set. Okay, yeah, I mean, I understand that. For example, what is the definition of a positive definite matrices? N by n, right? Okay, a set of n by n matrices such that A and, okay, this guarantees the symmetricity of the matrix, and then X transpose A, X, positive for all X in Rn. Yeah, so if you notice, there's the connection, like that type of set definition is not something we have no idea about, right? Okay, we can look into something that we know and correlate, how, okay, for example, this is, like, we are not saying in Rn, we are kind of restricting that, okay, but still, it's a similar idea. Another way it would kind of make things easier would be to give another name, right? And then write the thing that you know, and then check the terms one by one, right? For example, with this, we gave that example of like negative definite matrices, right? Yeah, it is quite similar to that, all right? So this claim states that this set is convex, and anytime we say convex, okay, we need to also say like convex with respect to what? With respect to this, like, and okay, A matrix, rather the entries of the A matrix. Okay, so we will be using these trace properties, and these are the type of things that, like, for example, cyclic property, and then a transpose, it doesn't change, and okay, so this requires 2-3 steps to figure that out, and then this is also kind of common sense property. Okay, so let's discuss why this is convex. All right, so I just wrote the set definition, okay, and then here, first of all, let's say that this is a scalar expression, right? Okay, and I can take the trace of this scalar, right? Scalar equals trace of that scalar. So, okay, we didn't do anything crazy. And I'm just distributing the terms, right? Basically expanding that expression, and linearity of the trace operator, I am separating them, Okay, and using the like we can basically cycle the terms. Like here we can take this term and then put it here. So we are basically doing that. All right, and then I'm looking at this. Okay, nothing is going to change in this route, and here, yeah, one more time I am taking that P1 term and then putting here. Okay, so this is where we are, and now I'm looking at, yeah, using this property, I'm writing that from here. Okay, got it. So, and in the final step, I'm just gathering the terms. Let me clean all that. So ATP, and these terms are like literally the same, and I'm just writing that expression as given. All right, so we didn't do any like crazy manipulation so far, and now we are introducing this expression m of x. Okay, the reason why we are introducing that will be clear in a second. So okay, we have m of x and trace. So let's recall this definition. I'm sure if you use or if you dealt with some type of optimization problem before, like in a, I think this is the type of stuff that you will see in like semi-definite STP optimization type of problems, right? Especially like deriving some of the properties, and I'm sure you must have heard like seen something like that, but it is not important. It's just a simple notation, and trace of A transpose B can be written like this, and probably you may not see that because F term, because they generally tend to like ignore that, right? But this is known as like Frobenius inner product. Like if you go to Wikipedia and then like this is the term that you need to search for. Okay, but again, this is a simple notation. That is it, like nothing more than that. All right. So here, this is where we are, and this is the set that we are looking at. Again, if this term is like confusing, you just like rename it, just some set. Okay, so let's record the definition of half space. All right, half space definition is like this set, of course, and is this. So A transpose X, and like now this term is scalar, and then this is just another scalar, and this is like we have inequality here. So this is the half space, typical half space definition, and if you can notice, like for a fixed X, let's say that is, I mean, this is it needs to be like a vector, but you give me a fixed X, and then this is the set that I would have, and then if you notice, this is quite like this is quite similar, quite an explanation that is similar to the half space definition, half space set. Let's say it that way. And why is that? So we have X and then A transpose X, and then we have inequality. All right. So instead of X we have A, right? And then we have inner product, and this is again like inner product theorem, and instead of this we could also write X, right? So okay, and then for a fixed X, this is a half space, and using that expression, we could write the original set. This is the original set in that way, right? And why is that? Anytime you have, I mean, it will not be a great explanation, but like set inside of sets, basically you can write it like that here. Okay. All right. So, I mean, this is some type of mathematical, I don't want to say skill, but like mathematical manipulation. Depending on your background, you might or might not have like seen that, which is understandable. But if you have never seen like a manipulation like that, just take a minute or however how much time you need to just sit back, relax, and then think about why it makes sense, right? And then yeah, after a while it will make sense. I'm telling you. So this is the set, by the way. We just like wrote the given original set in another way. Okay, this is another way of expressing the same set that is given to us. So using like we're gonna use like two key properties. A half space is a convex set. This is like known fact, right? Like everyone knows about this. And go to straight and then ask a homeless person. Even homeless people like would know about that. And I actually have a very fun conversation about that last week. So anyway, so the second property, maybe not homeless people, but an average people would know about that. Intersection of convex sets is a convex set. Okay, using those properties, first of all, we said that this was a half space, and then we are looking at bunch of half spaces, and then we are looking at the intersection of them, right? Something like that. I don't even know why I just drew that one sec. Okay, let me just eliminate that. So using those two properties, we can conclude that the original set A, math, cal, calligraphic A, right, is a convex set. Okay, so that was like the claim number one, and then we are done with that. We're going to look at two more claims, and then after that we are going to discuss another part of like that is related to the specific problem that we started discussing, right, about the PLDIs, linear, or rather, polytopic linear differential inclusion type of autonomous systems. Okay, so basically this claim is saying that when you have a given convex set S, okay, and you have n by n, a1, a2, dot dot dot, an terms. Again, this represents convex whole of those terms. So this represents a set, okay, obtained by taking the, computing the convex hull of those points. And then if you have that expression, this is identical to this expression. So first of all, from here to here, it makes sense. Like we have bunch of points here. I need to fill it, but anyway, okay, just imagine like this is filled, and here we are only looking at those points, right? Like for example, if every point, wait a sec, what type of, anyway, if every point in this set belongs to set S, then we would know that the vertices, of course, like they belong to S, right? Okay, I mean, that quite makes sense. The real issue is that why, implied by expression we have here. So, like the other direction may not make sense directly. But this basically comes from, I'm not going to go over the complete proof, but this comes from the fact that this set is convex, and then here we have, let me use my convex set drawing skills. So you give me any 2 points, and then when I look at all the points between them, right, they need to reside in the set. This is the set. So, I mean, this is like the convex definition. And because of that, like this part kind of makes sense. And this, where is it? Yeah, this proof goes over that. And of course, I'm gonna upload this PDF. If you look at it, this is very nice writing. Like I use overleaf and then, whoa, amazing. Okay, so I'm literally bragging about my notes now. So let's go over the claim that is similar to the previous one that we look at it. And only thing that is different is we have linear map here. Right? Let's go and then copy the previous one. Copy and then paste. This was the previous one, and then this is like claim number 3. So only thing that changed is this, we have linear map, right? And another way of writing is also this. So, well, we are like based on all the arguments that we, discussed, or like all the points that we argued. And here we are also arguing or using, like taking advantage of the fact that this map is linear, right? And then linearity has like very important key properties like homogeneity, and then what was the other one? Yeah, additivity, like those basic 2 points. And it basically comes from that, right? Okay. Another important thing to, I think, mention is that when you have a convex set, and if you take the linear map of it, okay, I'm gonna do a crazy thing. I don't know what type of linear, like what type of abstract space is this, but wait a sec. This, good job, notability. Anyway, so let's say this is a linear map, and let's say this is convex. This is linear, right? And then this is convex as well. This is a convex set as well. So, look, this is one of the properties, right? Okay. And so I'm not gonna, go over the details, but I'm gonna upload this PDF. It is amazing. Like I'm looking at it, and it's crazy that I wrote this. Anyway, so let's look at the claim. Now we are pretty close to like go over the complete proof. Here we are basically saying that AI, and then we have this is not AI, like this is the type of AI that you're familiar with. This is A sub I, and we have A1 and A2 n by n matrices, okay, and then we have strictly positive definite matrix P1, and then semi-definite positive matrix P2, and again we have actual, wait a second, yeah, I thought for a second there was a typo. This represents the convex hull of the sets, this set, okay, and TFAE, what does that mean? Means, anyway, I was going to make a joke, but it wouldn't land, so I'm not gonna. The following are equivalent. Here, these two expressions are equivalent. Let's go over and discuss why that is the case. So, this is the claim. This is the claim, and let's check the proof. First of all, I'm just writing the first expression, like the given expression 1, and I am expressing that in another way. Okay. It means, first of all, just like this expression and this expression is like same. It would be great for me to, I mean, I didn't want to rename it like math cal x or something. It would make things maybe easier, but I am the type of person that I would like things to look complicated, so I would feel smart, because I'm studying math and engineering, so I'm a very insecure person. And all right, that was a joke, everyone. So what should we do here? Okay, how would it make sense? First of all, that type of expression, that type of like statement, let's look at something that we are familiar with, right? I'm just going to write something. Yeah. Okay. So let's say we have this statement. Can you give me another statement that is equivalent to that statement? And the answer is, actually, you know what I'm going to do? Okay, I will, so for once in my life, I will try to make things up easier. So, yes. This is another expression, and they are equivalent. Like, I literally wrote the same expression in a different way, right? So, that equivalence is basically what we are doing. Here, again, this is the x set. Like, let's imagine if it is complicated for you for some reason. I mean, it may be, by the way, like I'm just, after you look at the same problem for the last 2 days, you tend to, get used to the terms. But you can change it with this, or I mean, Rn or something. So, okay. And we have that, but we are also keeping that. And so basically what I'm saying is try to ignore that. Okay. Again, if you recall, this like equivalence is quite similar. Like I'm talking about like the reasoning, right? Quite similar to this. So don't let it, scare you or something. And instead of writing that, I'm looking at this term a bar, and I'm basically writing that and stating that here, for example, we have the condition, and then we are saying that P matrix is in a set. So here in this set, I mean in this case, what is the set that a bar belongs to? We are basically writing that expression. Like literally we just wrote the same expression. Like we didn't do anything crazy, right? We are reasonable people. We don't do crazy things. So, all right, we are very boring actually. Okay, here, once we have the set definition, right? The question is, like, the big question is the set a bar belongs to? Like I'm even like making that clarifying that. So, is that set convex? And the answer might surprise you, or may not. Yes, the proof is given in claim 1. Like that is the first thing that we discussed. Another thing, let's check the following. Here, I think this is what we discussed in claim 2. Yeah, here we are basically saying that a bar is in convex sets. For all a bar takes values from this convex hull of that set. Okay, and this expression is equivalent to this expression. Again, this direction totally makes sense, right? And one more time, this direction comes from the fact that this set is convex, and we are using convex property, nothing more. Okay, and here I am trying to simplify things. This is x, and then this is the original term, right? And using this equivalence, that we discussed in claim 2, the following can be written. Basically, I'm literally like using the same expression. Like even the notation is quite similar to make things easier for you, right? Like what else do you want? Just leave me alone, all right? So where the term on the right hand side is equivalent to the expression 2, all right? I'm just taking a look at it. Instead of basically here, I just got rid of that convex hull, and I am only looking at the quote unquote I want to say vertices, but the points. Actually, that's an interesting point. Anyway, I'm not going to discuss that. So instead of looking at the whole set, right, and which is created by taking the convex hull of this like points, I am looking at those points only. That is it. So in a way, this was a like, if you were to check if that is correct, in theory you would have to look at infinite number of points, right? But here we are looking at finite number of points, so quite an achievement. Okay, so the final, this is like the one claim, and then after that we are going to go over the complete proof, which will literally take like, I don't know, 2 minutes or something, depending on how I emotionally feel about myself. So okay, this claim says that, one more time, we have the AI, not artificial intelligence, like matrices, and so 1 and 2, okay, and then we have a positive symmetric positive definite strictly and P1 matrix, and then positive semi-definite P2 matrix. Okay, and again this expression, this denotes convex hull of the sets of the points. All right, the following are equivalent: TF AG AE. So the expression 1 says that, I'm gonna be honest with you, okay, even now when I look at it, it kind of like I would need to take a second to think about what was it that. Like later I spent 2 days working on, first of all, understanding the problem, going over the like proofs, like dissecting, like trying to make it like how would I make that like easier. Like, I've been thinking stuff like that, and for a video that maybe like 5 people maybe would watch, but that's right. So here, this is the expression that again we are saying that this is not Rn, this is some subset of Rn, okay? And when X is in that subset, let's say when X is in this set, then this expression, this given term is correct. This given expression statement is correct. Okay. Here, that is inequality is correct for all the A bar terms. All right. And this is expression 1, and then expression 2 says something that it has nothing to do, or it may look like to some layperson and that this has nothing to do with what we are discussing here, right? And now we will discuss why that's the case. I understand that. Here we are saying that there exists lambda 1 positive such that this inequality is satisfied. If you recall, we didn't have any like lambda like scalar terms, and by the way, this is scalar and lambda terms. This is AND operation, and we also have like lambda 2 again for this A1 and then this A2. Okay, so this is really important, and now we will be discussing that, like why those two expressions are equivalent. All right, Like for example, let's say, you can imagine that this is the expression that we need to check to show that the Lyapunov function that we have, in fact, can be used to prove the stability of the given system. However, like if you can notice, this is quite not straightforward, right? But we have identical expression. And then this expression, like basically LMI, right? Lambda 1 terms are the terms that we need to find, but let's imagine that we have lambda 1 terms. Then we would come to the conclusion that in fact this is LMI, and then yeah, we can solve it in polynomial time. Not a problem. So this is very important, and then now we will discuss that. Let us start with I'm just writing the expression 1, right? Here, this is another way of writing the same expression. I'm just saying that, for example, this says that if x is in this set, then this is true, right? And then I'm saying this is true, this is true for all the x values that is in this set. Yeah, like they are identical. Okay. And as it is given in claim 4, this is equivalent to, this expression is equivalent to, this is something we discussed, right? And here we have a bar, and then we have a bar taking values from a convex hole. And here, this statement is identical to the statement where, instead of looking at the convex hole, the term that we have needs to satisfy the given inequality only in the some part of my brain, I don't know why wants to say a vertex, but the terms that we generated that convex hole set, right? Okay, instead of looking at the convex hole, or rather, instead of looking at every point in a set that is created by taking the convex hole of those points, we are only looking at individually the given points, like A1, A2 here. And okay, so in claim 4 we discussed that. And this expression, we have A1 and A2. I'm just writing it in an explicit way. Instead of saying that, I'm just writing, okay, A1 for A1 and then for A2. There's nothing more, right? And again, this expression, let's focus on this, because the other one is whatever that I will be doing will be quite similar to what I will be doing, like to that expression. So let's focus on the first term, and I'm just writing that expression in another way, right? And this is something that we discussed. This inequality holds for all x in this set. And then I'm saying that if x is in that set, this inequality holds. That is it, like they're identical, these statements. And by the way, like, if you are curious as to, are you sure? Yeah, I'm definitely, you can bet your whatever, that's, I'm sure. Okay, I just like look at every, identity, etc., every inequality. And yeah, at some point, that I'm hoping, like I didn't notice any typo so far, but I'm hoping that there's no typo, but the general vibe of the, these notes are like this video is correct, right? Or my feelings are pure. Like this is what matters in math. So, or in aerodynamic or dynamical systems in general. Okay, and yeah, I just wrote that way, right? This is identical. Again, I'm doing the same thing for those two expressions, and using the S procedure. Yes. So the reason why I needed to write it that way, because when I have the expression in that way, it is really easy to directly take advantage of the S procedure, right? And here, this is basic what we are doing. And then in the previous video, I discussed like a procedure, right? So let's look at this. And there is a if and only if relationship between this expression and then this expression, right? This is what S procedure tells us. And this is great, by the way. So far, if you notice, we have been using if and only if. So we didn't use, okay, this is the stability condition, and then this implies this. So, or rather, wait a sec. Oh my God, I was going to make a huge mistake. Anyway, this is the stability. Yeah, this is the stability. Let me just show one more time. This is stability, let's say, condition that we need to specify, but we have another like condition, and then that implies this. And we know that this is correct. Anytime you have something like that, you are satisfying something harder. Like this is basically, we are looking at a sufficient condition, right? We are basically doing that. We want to prove Q, and then we are looking at P implies Q, and then we know that P is correct, and then as a result of that, Q is what we have, and then this is called modus tollens, I think. Anyway, so I think it's Chinese, yeah, what I just said. Anyway, all right. So what I was trying to say is that we've been using if and only if, right? However, instead of this, if we use, let's say this is the stability condition that we need to specify, and then this is another condition that is identical to that, is identical, equivalent. And if this is correct, then we are basically specifying something that we need to specify, nothing more. Like it's not sufficient condition, so it's like there's no like conservatism type of problem that we will be dealing with, that whole world is dealing with at the moment. All right, so let's continue, and without making any random jokes. So this is the S procedure. This comes from this equivalence comes from the fact that we use S procedure, and I'm just basically changing like lambda 1 and lambda, like if you notice, this is all its own box, right? And then that was the reason basically I wrote this, I produced that lecture note, and then I'm making this video. Here, this is the following. And if you notice, we are not saying that there exists lambda, like one lambda, that's, and let's imagine that's not the case, and then let's imagine that's not the case, or wait a sec. Yeah, we can imagine actually, wait a sec, yeah. Okay. Let's imagine that it is the case, right? There exists lambda positive such that this and this are satisfied. Then this would be a harder thing to satisfy, right? I mean, if you need time to think about why that is the case, and just remember the difference between robust stability and then quadratic stability. In robust stability, for any given parameter, right? If you remember, like when we were discussing like robust stability, we have a parameter, right? And for any value of that parameter, if you can come up with a P matrix, like P from that Lyapunov function, then we would say that this is robust stability. But you can only do that if you are sure that that parameter will not change, right? Like that is a parameter, let's say some P, and then it takes value between 1 and 3 or something, and it is constant. Like it is something that's constant. You just don't know exactly what that is. That is it. And in that case, you can, conclude that robust stability implies asymptotical stability. However, if you say that like we have one parameter and then it takes values between 1 and 3, plus it is time dependent, like it changes. And in fact, quadratic stability, and then that is the thing that makes quadratic stability conservative as whatever. So is the following: we don't even impose any type of like rate limits on how p changes. P, this parameter changes between 1 and 3, and then we don't even say that, but it wouldn't change like crazy, you know, fast or something. We are even taking into account those conditions or situations, right? So that's why quadratic stability, what quadratic stability is satisfying is crazy, like hard. And depending on your system, it may not even be realistic. So why would you need to look at something, you know, conservative? Just look at something. Anyway, right. Yes, the main point here was this: if that was the situation, this condition is harder than the condition that I just deleted, right? Or like this condition. Why? Because here one lambda needs to satisfy those. So we are basically imposing more constraints on this lambda, right? And because of that, it would be harder condition, right? Because the let's say, yeah, I mean, I think this is a simple point. I don't need to go over that. Okay, so, and then this, I'm just changing the name from lambda to lambda 1, and then here from lambda to lambda 2 to, I don't know, make it clear or something. And this is the expression that we stated in expression 2. So this is, yeah, the complete. Here we have the QED. The complete, the proof is complete. All right, it's kind of late for me at this time. Anyway, all right, and where are we? Yep, let's check the final claim. Let's go over that in a very quick manner. Okay, so this is the system, and then this is the Lyapunov function. Again, these are the Lyapunov functions, or the conditions that the Lyapunov function satisfy in order for us to be able to prove the stability of the given dynamical system. And these conditions are equivalent to those conditions, right? Okay, and then we ask the question why, you know, a very, very, very annoying question if you think about it. And again, let's start with this proof. And then the Lyapunov function satisfy the following. These are the typical like stability conditions. And since this is strictly positive definite, the first condition, which is the positivity of the Lyapunov function, is satisfied. So that's great. Actually, it would be great if I have like some, you know, noise effects, like, you know, bunch of children saying "oh" or something. That would be like when I say, okay, this condition is satisfied, and then like people screaming like "oh, great" or something. Yeah. Anyway, okay, when I reach to like 10,000, I will be doing stuff like that, right, people? So keep subscribing or something. Okay, for the second condition here, this is the derivative, and the following should be satisfied, or this is equivalent to this. Why is that? Here, when we have, like, if you look at the nature of v of x, I'm not going to go over the detail because I discussed that in the previous video. And then this video, the purpose of this, or let me say something cool, raison d'etre of this video is to clarify some of the points that I didn't, I or basically glossed over in the previous video. And that is, yeah. So I'm only looking at that, like those parts. Due to the structure of v of x, right? If this expression is greater than this expression, then v of x would take, what was that? It was, yeah, something like this. Okay, and then you take the derivative of it, and it would be p a, but we have a bar, like we have a of t, and taking values from a convex hull of A1 and A2, right? Okay. So basically that is the reason, right? I explain due to the structure of v of x, we have this condition for like v dot, and since we have like there are two conditions that can happen, like either this expression is greater than this expression or the other way around, right? Okay, and when we have that situation, this is the condition, like this is basically v dot, and then this is v dot, and then we would like that to be like greater than equal to or less than equal to 0. So, and then a bar terms, they take the value from this convex hull set, and using claim 5, the first condition is equivalent to, let me change the color, and this condition is equal to this, right? And this is literally what we discussed in claim 5. And then again, this is like a cool thing, this is how you write back epsilon, and that means such that, and these are the type of things that you would use to make people think that you know math. In fact, you don't. So okay, again, we derive that this is equivalent to that expression, and again, like they are quite similar, and then because of that we can also write the same thing, and then in that case we would say like lambda 3 and then lambda 4, and for this second statement, and for the second condition the same method can be applied, and the following conditions, and finally we can have these conditions, right? So, and here we have the QED. All right, so these are the conditions that would for the Lyapunov system and then for the given dynamical system, and if you that you need to satisfy to prove the stability, asymptotic stability of the given system. That's it. So that concludes the video, and thanks for watching, and then don't forget to subscribe, and happy Father's Day, I guess. See you.